Right now, nothing in the observable universe is allowed to move faster than 299,792 kilometers per second. Not a rocket, not a signal, not a thought, nothing with mass, nothing carrying information. We call this the speed of light. That name is misleading. Light does not set this limit. Light is a passenger, one of the few things with no mass, and therefore the only thing naturally capable of reaching the maximum speed. The limit belongs to the fabric of spacetime itself. It is the maximum rate at which any change, any event, any cause, any consequence, can propagate through the universe. If anything moved faster, an effect could arrive before its cause. Time itself would run backward in some reference frames. The universe is not cruel in setting this limit. It is protecting the very thing that makes reality coherent. In 1865, a Scottish physicist named James Clerk Maxwell unified electricity and magnetism into a single set of equations. When he solved those equations, a number appeared that he immediately recognized. The equations predicted that electromagnetic waves travel at exactly 299,792 kilometers per second, already the measured speed of light. Maxwell had not set out to study light. He had been studying electric fields and magnetic fields. But his mathematics revealed that light itself was an electromagnetic wave. More remarkably, the speed appeared in the equations without any reference to an observer or a frame of motion. It came out the same regardless of who was measuring. This was deeply strange because in Newtonian physics, speeds add. A ball thrown from a moving train travels at the sum of its speed and the train's speed, relative to someone on the ground. Physicists assumed light must travel through a medium, something called the luminiferous aether, which set its absolute speed. In 1887, Albert Michelson and Edward Morley built an extraordinarily precise interferometer in Cleveland, Ohio, to detect Earth's motion through this aether. They split a beam of light and sent each half in perpendicular directions, expecting the two halves to arrive back at slightly different times. The result was zero difference. No matter which direction Earth was moving, the speed of light was identical in all directions. The concept of the luminiferous aether collapsed entirely. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would become the foundation of special relativity. Einstein began not with experiments but with two postulates. First, the laws of physics are identical in all inertial reference frames, frames moving at constant velocity. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. From just those two statements, every consequence of special relativity follows mathematically. And those consequences are violent to common sense. If c is constant for every observer, then time cannot be constant. Consider two observers, one stationary, one moving at high speed. Both measure the same speed of light. Since speed equals distance divided by time, and the moving observer covers more distance per event, their time must be running slower. This is time dilation. Moving clocks genuinely tick slower, not as a perceptual illusion, but as a real physical fact. At everyday speeds, the effect is immeasurably small. But as velocity approaches c, it becomes extreme. At 90% of the speed of light, a clock ticks at only 44% of its stationary rate. At 99% of c, it slows to 14%. A traveler at these speeds would age far more slowly than the universe around them. This is not theoretical. Atmospheric physics has confirmed it repeatedly. Muons are subatomic particles created when cosmic rays strike the upper atmosphere at roughly 15 kilometers altitude. They are unstable. They decay in about 2.2 microseconds. Traveling at 99.7% of c, they should disintegrate within 660 meters of where they were created. They should never reach the ground. But they arrive at sea level in vast numbers. From the muon's perspective, its own clock runs normally, but the contracted atmosphere is only 660 meters deep. From Earth's perspective, the muon's clock runs 13 times slower, giving it enough time to cross all 15 kilometers before decaying. Both perspectives predict survival, and the muons survive. The same principle scales up dramatically in thought experiments. Imagine two identical twins. One stays on Earth, one boards a spacecraft traveling at 99% of c. The traveler flies to a star 10 light-years away and returns. From Earth's perspective, the round trip takes roughly 20 years. From the traveler's perspective, with a Lorentz factor of 7 at 99% of c, the journey takes under 3 years. When they reunite, the traveling twin is 17 years younger than the one who stayed home. This is not a paradox. It is a prediction confirmed by atomic clocks flown on aircraft since 1971. Time is not the only thing that changes. Space contracts as well. An object moving at high speed is physically shorter, along its direction of motion, than when at rest. At 90% of c, a spaceship 1 kilometer long measures only 436 meters to a stationary observer. This is not an optical illusion. Space and time are woven into a single four-dimensional fabric, what Einstein called spacetime. Moving through space and moving through time are two aspects of the same motion through this fabric. The faster you move through space, the slower you move through time, and the more compressed your spatial dimension becomes. The mathematical quantity governing all of these effects is called the Lorentz factor, written as gamma. It equals 1 divided by the square root of 1 minus velocity squared divided by c squared. At everyday speeds, gamma is essentially 1. Newtonian physics is accurate enough. But near c, gamma climbs toward infinity. At 99% of c, gamma is 7. At 99.9%, gamma is 22. At 99.9999%, gamma exceeds 700. Every formula in special relativity, time dilation, length contraction, relativistic mass, contains gamma. Now we reach the reason why nothing with mass can ever reach c. As an object accelerates, it requires increasingly more energy to gain each additional fraction of c. This is relativistic mass increase. At rest, a proton has a mass of about 1.67 times 10 to the power of negative 27 kilograms. Accelerate it to 99% of c, and its effective mass is 7 times larger. At 99.9% of c, 22 times larger. At 99.9999991% of c, the speed achieved inside the Large Hadron Collider at CERN, a proton's effective mass is 7,461 times its rest mass. Every additional sliver of velocity closer to c costs more energy than the last. To push a proton all the way to c would require infinite energy. Infinite energy does not exist. The Large Hadron Collider is a ring of superconducting magnets 27 kilometers in circumference buried beneath the Swiss-French border. Its engineers must apply relativistic mechanics when designing the acceleration schedule for protons. If they use Newtonian equations, the beams would drift off course and the machine would fail. Relativistic mass is not a theoretical curiosity. It is a daily engineering constraint at one of the most complex machines ever built by human civilization. The same relativistic relationship produces the most famous equation in the history of science, E equals mc squared. It states that mass and energy are the same substance in different forms. 1 kilogram of matter, fully converted to energy, releases the equivalent of 21 megatons of TNT. The Sun converts roughly 4 million metric tons of mass into energy every single second. It has been doing this for 4.6 billion years. You already encounter the practical consequences of special relativity every day. GPS satellites orbit at 20,200 kilometers altitude, moving at approximately 14,000 kilometers per hour. Because of their velocity, their onboard clocks tick slightly slower than clocks on Earth, losing about 7 microseconds per day. A counteracting effect from general relativity makes their clocks tick faster by about 45 microseconds per day. The net result is that satellite clocks gain approximately 38 microseconds per day relative to clocks on the ground. This sounds trivially small. But GPS relies on timing signals to calculate position, and 38 microseconds of drift accumulates into roughly 10 kilometers of positional error per day. Every GPS satellite carries onboard correction algorithms derived directly from Einstein's equations. Without those corrections, your navigation app would be wrong by 10 kilometers before the day was done. Perhaps the most philosophically disturbing consequence of special relativity is the relativity of simultaneity. Two events that are simultaneous for one observer are not simultaneous for an observer in relative motion. Imagine a light flash at the center of a moving train car. For the passenger, the light reaches both walls at exactly the same moment. For someone on the platform watching the train pass, the light hits the rear wall before the front wall, because the rear wall is moving toward the light. Neither observer is wrong. There is no universal present moment shared by all observers. The concept of now is observer-dependent. This brings us back to the deeper question: why does C exist at all? The answer is causality, the principle that causes always precede their effects. In relativity, this is enforced by the structure of the light cone. From any event in spacetime, a cone of light expands outward. Everything this event can influence lies inside this forward cone. Everything that could have caused this event lies inside its backward cone. Nothing outside these cones can causally interact with the event. If information could travel faster than c, it could exit one observer's light cone and re-enter another's past, arriving before it was sent. The cause would come after the effect. C is not a speed limit for its own sake. It is the universal constant that preserves the causal order of reality. Physicists have imagined hypothetical particles called tachyons that would always travel faster than light. They have never been observed. More critically, tachyons would permit sending information backward in time, generating causal paradoxes, messages that prevent the conditions that sent them. The universe appears structured to forbid exactly this. Here is what all of this means for you, personally, right now. Every photon of light reaching your eyes is traveling at c, which means you are always receiving the past. The sun you see right now is 8 minutes and 20 seconds old. The nearest star beyond our solar system appears to you as it was 4.24 years ago. The Andromeda galaxy, visible to the naked eye on a clear night, appears as it was 2.537 million years ago. That light left its source before your species existed. There is a sphere surrounding you called the observable universe, defined by how far light has traveled since the Big Bang. Beyond that sphere, there is more universe. You will never see it. Not because it doesn't exist, but because C does not allow the information to reach you. Every observer in the universe has their own private observable sphere, slightly different from every other observer's. The actual present state of the entire universe, what is happening right now across all of space, is permanently unknowable. Not difficult to know. Unknowable in principle because the information cannot travel fast enough. And yet here you are, navigating, deciding, building relationships and civilizations. All of it from inside a bubble of old light, guided by a limit that prevents time from running backward. What you call now is a layered history of arrivals, each photon traveling at exactly 299,792 kilometers per second. The speed of light is not a wall between you and the rest of the universe. It is the rule that gives the universe a direction. Without c, cause and effect have no fixed order. Time has no arrow. Events cannot be assigned a definite sequence. With c, everything that has ever happened exists in an unambiguous causal chain. You, a temporary arrangement of atoms assembled by 3.8 billion years of chemistry, are a node in that chain. Every moment you experience is caused by the moment before it. Every choice you make is causing the moment after it. This is only possible because the universe has a speed limit. The speed of light is not a constraint on what you can do. It is the reason you can do anything at all.